Like what we did in Physics 1, when we looked at the motion of something, and we figured out the dynamics of it, and that sort of thing, we progressed into a treatment of mechanics in terms of energy. And here, where we're studying simple harmonic motion, we wish to do the same thing. We want to take a look at the energy treatment of the simple harmonic motion, in particular a mass on a spring. So let's take a look at that, the energy of the simple harmonic oscillator. Consider this. We have a mass on a spring and it's moving. So because it's moving, it's got kinetic energy. How much kinetic energy? Well, previously we figured out the position as a function of time and its velocity as a function of time. And we had that the velocity was equal to negative omega a sine omega t plus phi. So since that's the velocity of the mass, the kinetic energy should be 1/2 the mass times the velocity squared. So we have 1/2 mass omega squared a squared sine squared omega t plus phi. But we know that omega squared is k divided by m. So if we were to substitute that in for omega squared, the m's would cancel out, and we would get 1/2 k a squared sine squared omega t plus phi. Simply because omega squared is k divided by m. All right, so far, so good. Now the mass is moved, and by moving, it has compressed the spring, and it's compressed at a distance x. So because the spring is compressed, it is storing potential energy. So we wish to figure out what that potential energy is. We know what x is, because that's the solution of our differential equation. It's a cosine omega t plus phi. So the stored energy in our spring is 1/2 k x squared. And in this case, that would be 1/2 k a squared cosine squared omega t plus phi. So that is our stored potential energy. And if we ignore damping or any kind of frictional effects, we are either going to have kinetic energy plus potential energy. So our total mechanical energy will be the kinetic energy plus the potential energy. Bear with me. 1/2 k a squared sine squared omega t plus phi plus 1/2 k a squared cosine squared omega t plus phi. Factor out the 1/2 k a squared, and I have sine squared plus cosine squared of the same stuff, omega t plus phi. Anytime you have sine squared plus a cosine squared of the same thing, that's just a fancy way of saying 1. So our energy is indeed just 1/2 k a squared. Cool. So for a mass undergoing simple harmonic motion, the total energy at any particular velocity and any particular x is equal to 1/2 mass times the velocity squared plus 1/2 k x squared. But we just determined that our total energy would be 1/2 k a squared. So we have that 1/2 k a squared is equal to 1/2 mass times the velocity squared at any particular point plus 1/2 k x squared. And note that if we had this simple harmonic motion going on, in any case, at the point where it reached maximum amplitude, it's going to momentarily stop. And if that were to occur, then my velocity would be 0 at that point, my x would be equal to a, and I would have 1/2 k a squared equals 1/2 k a squared. I could have done that originally just to prove that my total energy should be 1/2 k a squared, because when my energy is totally potential, then it should be equal to 1/2 k a squared, and that would be my total energy at any other point as well. So that's kind of neat that that worked out. Okay, so I'm going to take this equation, 1/2 k a squared equals 1/2 mv squared plus 1/2 k x squared. I'm going to multiply both sides by 2 to get rid of the 1/2s. I'm going to solve this for velocity. So I'm going to subtract the kx squared from both sides, divide by m, and take the square root. So I have mv squared equals ka squared minus kx squared. Factor out the k, divide by m. And now if I take the square root of this, well, I'm one step ahead of me. K divided by m is omega squared. So velocity squared equals omega squared plus times a squared minus x squared. Now I'll take the square root. And my velocity then is equal to omega times the square root of a squared minus x squared. Now note that if I were at the position where x is equal to the amplitude, at maximum position, then I would have x is equal to a, and in the parentheses I would have a squared minus a squared, which would be 0, excuse me, and my velocity would be 0 at that point, which is exactly what it is. So when I reach maximum amplitude, I momentarily stop, my velocity is 0. So it fits that boundary condition. Also consider when x is equal to 0, I'm passing through the equilibrium point. So I had this oscillation going on, and when I pass through equilibrium, I should be at my maximum velocity. When x is equal to 0, then I have a squared, and the square root of a squared is a, so my maximum velocity is omega times a, and that checks out as well. So those boundary conditions make this formula work. And so this is a very useful formula for any particular time when I know what my x value is. I can find out what my velocity is at that point. It's a formula, I'm not sure you would find this in the book, so it's just one neat little formula to have. All right, based on energy, let's try a problem. A block of unknown mass is attached to a spring of spring constant 6.5 newtons per meter, undergoes simple harmonic motion with an amplitude of 10 centimeters. When the mass is halfway between its equilibrium position and the end point, its speed is measured to be 30 centimeters per second. Calculate the mass of the block. Well, let's set up our energy equation. We know that 1/2 Ka squared equals 1/2 Kx squared plus 1/2 mv squared. Get rid of the 1/2s. And in this case, we know that when we are at halfway between the equilibrium and the amplitude, at a position where x is equal to 1/2 a, or in this case 5 centimeters, our velocity is 30 centimeters per second. So we could plug in everything we know about this position. We're given k, 6.5. The amplitude is 10 centimeters, or 0.1 meters. Square that. Our x position is half that, 0.05 meters. Square that, times k. Plus our mass, which we don't know, but our velocity is 0.3 meters per second. Square that. I have all these values and our mass. Just by algebra, I can solve for what the mass is. In this particular case, it would be equal to 0.54 kilograms. What's the period of the motion? Well, I know that our angular frequency is the square root of k over m, so let's determine that. 6.5 divided by our mass, which we just determined to be 0.54 kilograms. The square root of that is 3.5 radians per second. If I know the angular frequency, I know the period. The period is 2 pi over omega, so 2 pi over 3.5 radians per second gives me a period of 1.81 seconds. What's the maximum acceleration of the block? Well, I now know the angular frequency, omega, and I know the amplitude, it was given before, is 0.1 meters. So my maximum acceleration is omega squared times the amplitude. 3.5 radians per second squared times 0.1 meters, 1.22 meters per second squared. Oops, I thought I had more there. Okay, so nice. That's an energy consideration of our system. You know, if the only thing we were to deal with was a mass spring system, then we just focus on that and not worry about this general treatment of a second order differential equation and solutions of that. We'd only deal with a mass spring system. But like we said in our introduction, there are many systems that exhibit simple harmonic motion. And so we want to do this general treatment of the second order differential equation to account for these other systems as well. Another example of simple harmonic motion, as we mentioned, is the pendulum. A repetitive motion about an equilibrium point at the bottom here, and we want to prove this is indeed simple harmonic motion. So let's take a look at a pendulum. A pendulum is a mass on a string like this, which keeps the string taut, and we just start this motion from some pivot point in oscillatory motion back and forth. It extends through an arc. We'll say the arc length is S, and the radius of our arc is the length of the string, which is L. So at some particular point, when this is at an angle, we have the force of gravity pulling straight down, but a component of force along the arc of the swing is mg sine theta, and the other component is mg cosine theta, which is being balanced out by the tension in the string. So the only force that's restoring this ball back towards the equilibrium position is that tangential force, the mg sine theta. So we can say by Newton's second law, mass times acceleration should equal the net force, and we have mass times our second derivative of the arc position, S, with respect to time, is equal to that net force, negative mg sine theta. Negative because it's back towards the equilibrium position. We'll note that our arc length is equal to the radius of the arc, in this case L, times the angle theta. That's true of any arc length. And if our angles are small enough, the sine of theta will equal theta. You can prove this to yourself by using radians, but if you're dealing with an angle, say less than 15 degrees, and deal with the radians, which would be on the order of 0.1 radians, put that in your calculator in radians mode, take the sine of 0.1 radians, and you should get something very, very close to 0.1, and that's just the limit of our small angle approximation. So we're going to substitute in for our sine theta the value theta, and substitute in for S, L times theta. So now our differential equation looks like this. M times L, second derivative of theta with respect to time, is equal to negative mg times theta. Get rid of our m's on both sides, divide through by L, and now I have this. The second derivative of the angle theta with respect to time is equal to a negative constant, g, which is 9.8 meters per second squared, divided by the L times theta. So we relate the second derivative with the theta itself. And we have set up our famous second order differential equation. Through this, we can identify that what's in front of the theta should be our omega squared. So our omega squared for this example is g divided by L. So omega is the square root of g divided by L. Once we determine our angular frequency omega, then all of our treatment of simple harmonic motion that we've developed before follows from there. The only difference is we have a different omega. For the mass spring system, we had a square root of k over m. For the pendulum, we have the square root of g over L. But once we establish that, we can get our period, our frequency, and everything else that we need for our motion from that. So here's our frequency, omega divided by 2 pi, which is 1 over 2 pi square root of g over L. And then our period is the 2 pi times the square root of L over g. Kind of interesting side fact of this is that if this is our pendulum with a definite period being going there and back again, back to our original position, that the period only depends on the length of the pendulum. If we're, say, on the surface of the Earth, g being a constant, the period is only going to depend on the variable of the square root of L. So that would say that regardless of my amplitude of this motion, that the period there and back again is still going to be the same. So this is a relatively good timekeeping device for like a grandfather clock, in that if the amplitude were smaller, that period there and back again is still the same as the period when the amplitude is larger, there and back again. How about that? I want you to study this motion very carefully. Study it very, very carefully. You will study your physics. You will study your physics. I'm going to use any kind of method I can to bring my teaching across. Just understand that. Okay, so let's try an example. A man enters a tall tower needing to know its height. He notes that a long pendulum extends from the ceiling almost to the ground, and that its period is 12 seconds. How tall is the tower? All right, very good. So this guy enters a tall tower. He extends a pendulum all the way to the ground, sets it oscillating, and measures the period to be there and back again 12 seconds. Based on this, how tall is the tower? So he wants to use the engineering approach rather than just extending this all the way to the ground and then pulling it up and measuring the length of the pendulum. So maybe he's across the street and he's observing this pendulum go from across the street. Okay, so we'll give him that benefit of the doubt. We know in general the period of the oscillation should be 2 pi square root of L over G. Let's reverse engineer this and solve this for L. So we're going to square both sides, multiply by G, and then divide by 4 pi squared. So we have L is equal to G times T squared over 4 pi squared. G is 9.8. The period was measured to be 12 seconds. Square that over 4 pi squared. And the length of this tower is 35.7 meters. Let's try another problem. A simple pendulum has a mass of 0.25 kilograms and a length of 1 meter. It is displaced through an angle of 15 degrees and released. So we're just on the border of our small angle approximation. What are the maximum speed? Now, if we're looking at simple harmonic motion, we would expect the maximum speed to occur when it goes through the equilibrium point, in this case, at the lowest position of the pendulum. So we're going to hit maximum speed at that point right there. But if we want to use the approach of simple harmonic motion, we could find omega, find the amplitude, and the maximum speed should be omega times the amplitude. So that's where we want to go with this. So we have a small angular displacement. Omega is going to be the square root of G over L. We have a 1 meter long pendulum. So the square root of 9.8 divided by 1 is 3.13 radians per second. Our amplitude is going to be the length of our arc. That's going to be equal to the radius of the arc times the angle theta in radians. The length, or the radius, is 1 meter. The angle theta in radians is going to be 15 degrees converted to radians. We know there's 2 pi radians and 360 degrees. So that's going to give us an amplitude of 0.262 meters for the length of that arc. Omega times A is our maximum velocity. So 3.13 times 0.262 meters is 0.819 meters per second. We did the same problem in Physics 1 where we used conservation of energy there based on potential energy of height, mgh, and then all that potential energy should be converted to kinetic energy at the bottom. We solved for the velocity there. If we use that same technique of Physics 1, we would have gotten a very, very similar answer here. What's the maximum acceleration? Well, that's omega squared times A. 3.13 radians per second squared times 0.262 meters, 2.56 meters per second squared. The maximum force is the mass times the maximum acceleration by Newton's second law. The mass was 0.25 kilograms, so if I multiply that by the acceleration we just got, 2.56, I get 0.641 newtons. Right, so that was a pendulum. But I could even have a physical pendulum or another system involving oscillatory motion. Now, a physical pendulum might be some kind of object like a hammer or like this meter stick, where I would have this oscillation based on its rotation about a pivot point based on the torque causing that oscillation. So we'll consider a physical pendulum where the pivot is located at the end here, and the center of mass is where the action of the external force is acting on, in this case gravity. So if I had this hammer and we had a center of mass, gravity acting at the center of mass, our moment arm is the distance from the pivot to the line of action of that force. So in this case, the line of action is vertical, and the shortest distance from the pivot to that line of action, in this case, is going to be equal to the length to the center of mass times the sine of this angle theta, theta being the angle that this pendulum is making from vertical. So I would set up this kind of equation. My net torque, which is the moment of inertia times the angular acceleration, is equal to my force times moment arm, at least negative force times moment arm, because it's restoring it back towards equilibrium. And that's my only restoring torque. And in this case, I would say then that since angular acceleration is the second derivative of the angle with respect to time, I can put in my force, which is mg, and my moment arm, which is L times the sine of theta. Using a small angle approximation, sine of theta being equal to theta, we have now that the second derivative of theta with respect to time is equal to a negative mgl divided by the moment of inertia I, whatever that is, times theta. And I have set up, again, my second order differential equation, which designates simple harmonic motion. Now I can look at the constant that's in front of the theta, and that is my omega squared. So I now have a second order differential equation where omega is equal to the square root of mgl over I, and I can solve that system in that way. So my period will be equal to 2 pi over omega, 2 pi times the square root of I over mgl in this particular case, L being the distance to the center of mass from the pivot. Let's possibly set up an experiment for this. We can measure G this way. Excuse me. From a pivot with a meter stick. If I were to extend it out an angle like this, we could use this previous determination. Our distance L in this case is going to be this distance D, because our center of mass is right in the center of this meter stick. So a period should be equal to 2 pi square root of I over mgd. Now the moment of inertia for a meter stick is the moment of inertia of a thin rod about its end. And if you recall from physics 1, that should be 1/3 ml squared. With D being equal to 1/2 L, and the moment of inertia being 1/3 ml squared, we substitute that in to this equation and reverse engineer to find G. So I'm going to square both sides, solve for G. G will equal 4 pi squared I over 4 mdt squared. Substitute in for I, 1/3 ml squared. Substitute in for D, 1/2 L. M's cancel out, and one of the L's cancel out. And I finally get this nice expression here. G should be equal to 8 pi squared L over 3t squared. Try it with the meter stick. Your L is going to be 1 meter. T is your period of time. So measure this time, there and back again. Probably do it over several periods. So just get somebody to get a stopwatch, measure this over several periods, and see how good a value you can get for G. Just a fun thing to try. I tried it on a very crude measurement right before class, and I got a value of around 11 meters per second squared. So very crude, but I got a decent value, at least good enough for physics, decent value for the value of G of 11 meters per second squared compared to 9.8. So not too bad. So that concludes the second lecture on Chapter 15.